Okay, well, welcome back to the final 3 lectures of the semester. I guess if you're here, you probably already are aware of the fact that the grades are posted online. The exam 3 scores are posted online, as well as the fourth grade after the first 3 exams. So the way it works, as stated on the syllabus, is that out of the 4 exams, including the final, you drop the lowest grade. So if y'all don't go for the final, that would technically be a 0, it would be dropped, and then you would get exactly the grade that's posted here along with your code number. Because this is your grade after the first 3 exams, so if you don't take the final, that would not be included, and you would actually get this particular grade. Okay, so we're going to go ahead and continue working our way through into chapter 14 now. We basically already covered all of the planets, and what we have left to discuss is the formation of the solar system, this leftover material that makes up comets and asteroids, and the formation of the sun. Okay, so basically, the formation of the solar system turns out to be a pretty darn efficient process that really utilized by far most of the material that was available for the formation of planets. There's very, very little left that was not incorporated into a planetary body. So this material that's left, we call interplanetary debris, left over from the formation of the solar system. It's actually primordial. There's sort of different levels of primordial. We'll talk about that. But it basically represents material that hasn't been reprocessed very much since the formation of the solar system around 4.5 billion years ago. So this material, as it says here, ranges from rather large objects like comets and asteroids all the way down to the microscopic dust, which actually forms the shooting stars that we see if we go out at night and we see shooting stars. The rocky material that we see in planetary, in asteroids and meteorites actually is very similar to the outer layers of terrestrial planets. This is asteroid Icarus, which is a very large asteroid. It's one of the largest asteroids with a diameter on the order of 1,000 kilometers. So it's sort of like a continent in space, floating around in space. And the reason we're looking at this particular slide here is because what we see is a motion relative to the background stars. Okay, so this is actually a single time-lapse photograph where we're tracking the stars using an equatorial telescope now. And clearly, what we're seeing there is a streak, which means that that object is not a star, it is in fact an orbital body. Now, if we were to look at planets, we would basically need sort of multi-day exposures, but asteroids close to the Earth orbit pretty quickly, so we can actually see the trace being made. So as I mentioned, if we add up the mass of all of this material, it's not very much. It's actually less than the mass of the moon. So we're talking something on the order of 10 to the 25 grams in total for all this leftover material. So the formation of the solar system, the formation of planets and moons, was an incredibly efficient process. There's probably less than something like maybe a billionth of the original material left in the form of this debris. By far most of it was used up. Oh, this is sort of interesting, just to mention real quickly. Here's a photo of a comet, and what we're seeing is, in this case, we're seeing streaks for the stars, because what we're doing here is we're actually following the comet to take this photo. And because we're tracking on the comet, and the comet's orbit around the sun, the stars are a little bit smeared out. So it's kind of like the reverse of what we were looking at when we look at Icarus. In the case of Icarus, we were tracking the stars, so Icarus was smeared out because it's moving relative to the stars. And for this comet, we tracked the comet, so the stars are a little bit smeared out. But anyway, this shows you again that comets also are objects that are in orbit around the sun. All right, so speaking of comets, we have objects that are made of ice and rock. They're very primordial. We could say that they're essentially completely primordial because they are composed of some ices. And remember that the reprocessing that can occur usually results in the formation of larger protoplanetary bodies or actual planets. And when planets form and stuff gets crushed together, you get melting and heating. And so ices don't survive that process for the most part. So when we look at comets and we're seeing bodies that are icy and rocky, we're pretty much guaranteed to be looking at very primordial material that's really been essentially unchanged since the formation of the solar system. So comets have a special niche in that sense. And in fact, we're even interested in trying to explore comets by sending spacecraft there because they are little microcosms of the material that was present when the solar system formed so long ago. The other interesting thing about comets, which is actually connected with the fact that they're so icy, is the fact that they have very eccentric orbits. You can see that indicated here. The orbits are actually much more eccentric than what I've indicated here. If I really put in the correct eccentricity, it would almost look like just a line extending out from the sun. So this is sort of, something that I drew this way so that we can see the shape. But anyway, the connection with the icy composition is the fact that comets don't spend much time near the sun. That's why they can actually survive with an icy composition. And as we'll see, only a small fraction of comets even approach the sun at all. Like this one here, it's probably a 1 in a million comet that happens to have an orbit that takes it close to the sun. Most of the other comets out there spend their time in the outer solar system far from the sun. And so they don't form the types of cometary sort of appearance that we're used to with the tails and things like that. Okay, two major groups, short period and long period comets. We'll talk about those. This is an example of comet Ikeya-Siki. Now that I look at this, I should have shown another, actually a cat photo. You don't like to show cat photos because I have a cat who has a tail that looks a lot like that, except it's black. But not having noticed this until just now. Well, actually, you can see a photo a little later. So keep this wispy tail in mind. Anyway, the tail that we see there, there's a couple of things going on here. First of all, this is an object that's pretty close to the sun. That's obvious because you see that sunset or sunrise occurring over there. I don't know whether it's sunset or sunrise, but you can see the glow from the sun. So the point is that this particular comet is actually not that far from the sun because, we're sort of seeing it near sunrise or sunset. And that's typical for comets that have these big glorious tails because the tails form when the comets are relatively near the sun. Another point to notice, the tail is actually curved. Okay, so we'll talk about what's going on with that. Not only can we get curved tails, but we can even get multiple tails. If we look at this photo, we can pretty clearly see a bluish tail and this curved whitish tail. The bluish tail, is straighter. Okay, it's a straighter looking tail than the curved whitish tail. And we'll talk about what's going on there that actually represents different particles that are coming off the comet as it melts. Okay, different types of particles will kind of form these tails in different ways. We'll get into. All right, so the point of this particular chart is just to show that we're talking about scales here that are going way, way into the outer solar system. There's actually two kinds of scales that we're interested in here. There's two groups of comets, which I already mentioned. There's what we call the short period comets and the long period comets. Okay, the short period comets live around the orbit of Neptune. So we're talking orbital periods of, roughly 100 years out there, 80 to 100 years. And that's considered a short period comet. Okay? The other group of comets is not depicted on this table at all because they actually live, for the most part, way out beyond Jupiter, not Jupiter, but Pluto. So far out beyond Pluto that their orbital timescales are measured in the thousands of years. So these are the two types of two groups of comets. We'll get into that. I'm just kind of introducing general concept at this point. So moving on to asteroids, we're talking about small rocky bodies. So these are completely different from the comets because they're primordial rocky in composition. And their densities are therefore higher than the densities of comets. Most of these asteroids are smaller than 300 kilometers. 300 kilometers is still a pretty darn large rock to have flying around in space, unchaperoned, unsupervised in any way, and possibly on an orbit that would actually strike Earth. So 300 kilometers, an asteroid that size, is still large enough to do incredible damage if it struck a population center on Earth or something like that. Just for reference, if we're talking about asteroids large enough to cause things like extinction events, like what we think happened to the dinosaurs, you may have noticed that we don't see too many dinosaurs. Well, we get off the Beltway, we don't see too many. Well, that extinction event, you might be familiar with what happened there. That was actually due to a very large asteroid, maybe as large as a kilometer across, a big one. But even that asteroid that caused the dinosaur extinction is not anywhere near the largest ones that are out there.